Hey everyone. So today we are talking about formal charges. We are now bumping up Lewis structures to a whole nother level. We no longer can use those rules that we were using where we take octet electrons minus valence electrons to give us our bonds. We now have to use something totally different called formal charges. But before we get into that, there's a couple things that we got to talk about first that are really, really important, such as the phrase likes dissolves likes. Okay? That just means polar substances are going to dissolve polar substances, non-polar substances are going to dissolve non-polar substances. That's what that means. So polar dissolves polar, or non-polar dissolves non-polar. Okay, we see this so much in our daily lives. Okay, if you are cooking and you get butter on your hands, okay, butter is extremely non-polar. If you try to wash it off with just water, it won't come off because water is polar. Okay, water is polar, butter is non-polar. If you go ahead and you try to wash that butter off with just water, it's not coming off. What you need is soap. And soap is really, really awesome because it's got this head on it. So it's like this long chain molecule, this soap is, where all these chains of molecules are non-polar, but it will, on the end, have a polar head on it so that it can dissolve pretty much anything. So if you got grease on your hands, if you got butter on your hands, that soap can go ahead and break that down, so then that water can go ahead and wash it off of your hands. Okay? If you throw a rock in water, it doesn't dissolve because water is polar, the rock is not. Okay? Your skin has oil on it. Okay? If it didn't, then water would be able to just dissolve you away. Okay? Water is one of the best dissolving agents of all time. The fact that everything in the world doesn't dissolve from it is pretty amazing. So, polar, non-polar, likes, dissolve, likes. Remember that. That also explains why our ink on our chromatography papers moves up, right? If the ink is polar and the solvent is polar, it'll move it a lot. If the ink is polar and the solvent is non-polar, it won't move it very much. Okay, so that's the first thing I want to talk about. The next thing we have to talk about are resonance structures. Okay, there's these things called resonance structures. Okay, resonance structures. There's could be sometimes more ways to write a Lewis structure, more correct ways. Okay, so it's just different ways to write a Lewis structure. And really what it is it's just moving a double bond around on a Lewis structure. So if we look at a Lewis structure, a real simple one like NO3, okay, this is the Lewis structure for NO3. And some of you might put the double bond here. Some of you might put the double bond down here. Some of you might put it over here. Those are all correct ways to write this Lewis structure. And those are called resonance structures. They're the same. They just move the double bond around. Okay, so a resonance structure of this Lewis structure could be this. Okay, another resonance structure of this Lewis structure could be this. Okay, in this situation, all of these are right. They're all the best Lewis structure for that Lewis structure. They could be either one. These are resonance structures. You'll learn a lot about this when you take organic chemistry someday. But we might get in a situation where we need something different, where we need something that is not, or something that we might have multiple double bonds, or we could have single bonds somewhere, and it looks a mess, okay? And we'll have to choose between one or the other, and that's where formal charges come in. So let's go ahead and let's talk about formal charges, okay? Formal charges they are the charge on an individual atom in a covalent bond. Okay? And this is where we start to see a lot of our polyatomic ions, like SO42 minus or NO3 minus. You guys might have been thinking, these are all covalent bonds. Why do they have a minus? Why do they have a charge of a minus? Why does ammonium have a charge of +1? Okay, it is because of formal charges. And the way we figure out formal charges is valence electrons minus surrounding electrons. And you will know what I mean here in just a second. Okay, so let's go ahead and let's just get some practice identifying formal charges on certain atoms. And then after that, we'll do some Lewis structures to help us figure it all out. So let's look at something like COH2. Okay, I want you to figure out the formal charges on each of these atoms in this compound. So what we do is we take valence electrons minus surrounding electrons. Valence electrons are easy. We just go to the periodic table and we look at what column it is in. Surrounding electrons are a little bit different. Surrounding electrons are a bond or a dot. Okay? So this counts as one surrounding electron. 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 That dot counts as one. This dot counts as one. This dot counts as one, and this dot counts as one. So typically, right, when we're talking about how many they're surrounded by, we treat the bonds as two, but now we're treating every mark as just one surrounding electron. So now each bond is just one, each dot is just one surrounding electron. So let's go ahead and figure out the formal charge on this hydrogen. Hydrogen has one valence electron. How many surrounding electrons does this hydrogen have? It has no dots around it, but it does have one bond, right? Remember, we count that bond as one electron. 1 minus 1 equals 0. So the formal charge on this hydrogen is 0. Okay? You could say the same thing for this hydrogen, right? One valence electron is just surrounded by one bond. It's also got a formal charge of 0. That's a 1 minus 1 equals. There you go. Let's look at carbon. Carbon, we look at the periodic table. It's in the 4th column. It has 4 valence electrons. Let's go ahead and let's count up how many surrounding electrons there are. Each bond is 1, so 1, 2, 3, 4. Surrounded by 4 electrons, so it also has a formal charge of 0. Now let's go ahead and figure out the formal charge on oxygen. Oxygen's formal charge is, our valence electrons is 6. It's surrounded by 1, 2, 3, 4, 5, 6. 6 surrounding electrons. So its formal charge is also 0. Okay? This is a happy compound. That's what you want. You want the formal charges to be 0. Sometimes you can't help it. Okay? In all instances, you want to try to get the central atom to have a formal charge of 0. Sometimes it just doesn't happen. Okay? It's a big bummer. But that is how it is. So if we can, let's make that formal charge 0 on everything. If we can't, try to have it 0 on the central atom. If not, it is what it is. Sometimes it happens that way. So let's go ahead and let's look at a formal chart or a Lewis structure that we focused on yesterday, which was NH4+. All right, NH4+. So now, this will be one of those situations where the central atom won't have a formal charge of 0. But yesterday we did our rules, right? Which works for this. But it won't work every time, so now we have to draw a Lewis structure just based on this compound that they give us in the charge, okay? We have to match this charge with our formal charges, okay? Those formal charges will have to have a +1 somewhere in that total atom to match that overall charge. So now we're not doing our rules, we're just going to it. We're drawing our Lewis structure. We know N has to be in the middle, and we know H's have to surround. That's just a matter of fact. H will never be in the center, and we're just going to put a single bond to everything and see how this goes. Okay? Let's go ahead and count the formal charges and see how everything is for right now. Hydrogen, right, is surrounded by, or has 1 valence electron, and it is surrounded by 1 electron. That bond counts as 1 electron, so it has a formal charge of 0. So that means all my hydrogens are surrounded by a formal charge of 0. Okay, you don't have to put that on the Lewis structure, it's just good to help you keep track. But let's look at nitrogen now. Nitrogen has a formal charge, or a valence, I'm going to do that the whole time, has 5 valence electrons, and it is surrounded by 1, 2, 3, 4 surrounding electrons. So now it has a charge of 1 plus 1. So if I look at this whole atom, yeah, my central atom has a +1 charge. That's a bummer. Okay, it's not too happy. It'll probably react with something real soon. But that's the only thing we can do. And it matches my overall charge of +1. So we have the correct Lewis structure. Okay, we have the correct Lewis structure right now. What you'll end up doing is, to show that this has a +1 charge, is you'll usually see that they get rid of these formal charges, and what they do is they put this whole thing in square brackets, and they put the plus sign on the outside. You don't see that too often, but it does happen. Okay? So, AP exam, they'll be asking you to draw the perfect Lewis structure based on formal charges. You'll have to do this a lot. Okay, let's look at a couple more examples. Let's look at PO4 3 negative. Okay, now this is where the octet rule is out the window. Yeah, phosphorus is in the 3rd row. Okay, I can't guarantee anything following the octet rule after the 2nd row. Okay, carbon, nitrogen, oxygen, fluorine, they're always going to follow the octet rule. Okay, chlorine most of the time is going to follow the octet rule. Sulfur and phosphorus sometimes are going to follow the octet rule. Okay, so all I can guarantee you is that carbon, nitrogen, oxygen, fluorine, and chlorine are going to follow the octet rule. That's all I can guarantee you. Everything else is up for grabs. Okay, sulfur sometimes disobeys it. Phosphorus disobeys it. Xenon disobeys it. Even though it's a noble gas and doesn't like to react with anything, it will sometimes. Okay, so that's all I can tell you. Let's go ahead and let's look at this guy. We have a 3- charge that at some point we're going to have to match up with. Okay, so let's go ahead and let's start drawing. We know phosphorus has to be in the middle, and each oxygen is going to be on the outside. Okay, they like balance. It's not going to be like this. Okay, that's too spread out. It's not going to like that piece of stuff. Okay, so let's go with this, and let's just start with drawing a single bond to each oxygen. And let's go ahead and fill the octets on those oxygens. We know those oxygens follow the octet rule. Okay, oxygens, carbons, nitrogens, fluorines, and chlorines. That's all I can guarantee you. It's going to follow the octet rule. Okay, now let's look at our formal charges and see if this looks pretty nice. Okay, let's go ahead and do that. So, oxygen likes to have 6 valence electrons. And right now, each of these oxygens is surrounded by 1, 2, 3, 4, 5, 6, 7. 7 surrounding electrons. So each oxygen is going to have a -1 charge. Okay, that's -4. But before we do anything, let's check out phosphorus. Okay, phosphorus likes to have 5 valence electrons and is surrounded by 1, 2, 3, 4. So it has a +1 charge. Hey, guess what? That matches up with our overall charge, right? -1, -1, -1, -1 is -4, +1 is -3. But here is the tricky part. Is there something we can do to make the central atom 0? Let's give it a shot, okay? Let's try to make that central atom 0 if we can, okay? Especially now since we can disobey that octet rule with some of our atoms. So let's go ahead. What you start doing is just put a double bond somewhere and see what happens. So if I'm going to go ahead and put a double bond here, okay? Remember, oxygen doesn't disobey the octet rule, so let's go ahead and get rid of a lone pair to make it happy. So now, let's look at our formal charges. These oxygens are still -1, nothing's happened with them. But let's look at this oxygen, right? 6 valence electrons, it's surrounded by 1, 2, 3, 4, 5, 6 surrounding electrons. It's got a formal charge of 0. Cool. Okay? Now let's look at phosphorus. Remember, it likes 5 valence electrons. It's surrounded by 1, 2, 3, 4, 5. Now it has a formal charge of 0. And look at that. Our central atom now has a formal charge of 0, and we have matched that overall charge of 3-. So that is the best resonance structure for this Lewis structure. Remember, octet rule is out the window except for carbon, nitrogen, oxygen, fluorine, and chlorine. That's all I can guarantee you. Sulfur, maybe. Sulfur, maybe. But anything else is fair game, including phosphorus. Okay? So remember that when we are drawing Lewis structures. We're going to have to do this a lot. Let's go ahead and look at another polyatomic ion and see what we can do with that. Okay? Let's look at NO3 negative. Let's see what causes that negative charge on NO3. So, NO3 negative. Let's see what we can do here. Okay? Nitrogen's going to go in the middle. Oxygen's on the outside. And let's just start putting single bonds in there. So, 1, 2, 3, and all these guys follow the octet rule. Right? I could guarantee you that these guys follow the octet rule. Right? Let's go ahead and figure out formal charges. All these oxygens are the same, so that's nice. 6, 1, 2, 3, 4, 5, 6, 7. So all these oxygens have a -1 formal charge. Okay, now let's look at nitrogen. Nitrogen has wants 5 valence electrons, and it's got 1, 2, 3, 4, 5. So it's got a formal charge of 0. So that's nice. It's happy, but here's the issue. Our overall charge doesn't match our formal charges, right? We have a total charge of -3. That doesn't match our -1 charge. So we got to go ahead and we got to do something different here. Okay? So, again, the only thing that we can really do is just add a double bond somewhere. Let's go ahead and add a double bond to that top guy. So we'll put a double bond here. Again, these guys follow the octet rule, so let's go ahead and see what we got here. Oxygen likes to have a double bond to it. You'll start seeing that trend. Sometimes it won't, but if it could get a double bond to it, then oxygen's super happy. So anyway, 6 valence, 1, 2, 3, 4, 5, 6. Oxygen has a formal charge of 0 now. And nitrogen, right, it likes to be 5, and it has 1, 2, 3, 4. So now it has a formal charge of +1. Okay? Hey, this looks good as far as overall charge, right? It matches the overall charge of -1, right? -1 plus 1 equals -1 overall. The only problem is that our central atom isn't 0. Let's see if we could find a Lewis structure that satisfies the overall charge and makes our central atom 0. So let's try one more. Let's keep this guy on standby, just in case. Okay, so I'm going to leave him there, but let's do another one where we just do an extra double bond on nitrogen. Okay, so let's go ahead. We know that these oxygens are 0 from our previous example. We know that these ones with a single bond are -1. And let's look at nitrogen. Okay, 5 valence electrons, it's surrounded by 1, 2, 3, 4, 5. Hey, it has a formal charge of 0. So technically, okay, this would be the best Lewis structure. Central atom 0 matches the overall charge of -1, but nitrogen isn't following the octet rule. Okay, this is a situation where this guy is actually the better choice. Okay, I know that's a lot. I know you just saw me say with phosphorus that, okay, it could disobey the octet rule, right? But nitrogen won't. Carbon, nitrogen, oxygen, fluorine, chlorine definitely won't. Everything else is up for grabs. It could disobey the octet rule, but nitrogen can't. And it's disobeying the octet rule because it's got 2, 4, 6, 8, 10 electrons surrounded by its central atom. It's just too small, okay? It's too crowded right there. Those electrons, there's not going to be 10 in its outer energy level. Okay, that doesn't make nitrogen very happy. All right, so again, this is just part of the razzle-dazzle that goes with Lewis structure. So this guy is actually our best guy, okay? Again, all I can guarantee you is the octet rule only applies to carbon, nitrogen, oxygen, fluorine, and chlorine. Okay, let's do another one. Let's do SCN. SCN. Okay, so here we got 3 atoms. One of them needs to be in the center. Which one's going to be in the center? Usually the one that's least electronegative. Well, the one that's farthest left is carbon. So carbon's going to be our central atom. It likes to be the central atom, okay? And then we have S and N, okay? And this is going to have a -1 charge. Sorry about that. It's going to have a -1 charge. Let's just start by putting a single bond between each atom and filling their octet. Okay? We know nitrogen follows the octet rule. We know carbon follows the octet rule. Sulfur follows the octet rule for the most part. There are a few exceptions. Okay? Let's count up formal charges, right? Sulfur likes 6. 1, 2, 3, 4, 5, 6, 7. It's got a -1 charge. Carbon likes 4. 1, 2, 3, 4, 5, 6. It's got a -2 formal charge. Nitrogen likes 5. It's got a 1, 2, 3, 4, 5, 6, 7. -7 equals -2. Oh, there's way too much negative stuff going on here. We got too many surrounding electrons. We need some bonds in there to get rid of those surrounding electrons. So let's go ahead and put a double bond in there. Let's just go ahead and put one on this left side first and see what happens. Let's get rid of lone pairs so that they each follow the octet. Okay, now let's do formal charges. Again, sulfur likes 6. 1, 2, 3, 4, 5, 6. Hey, 0 for sulfur. That looks good. Carbon, 1, 2, 3, 4, 5. Carbon only likes 4, but it's got 5 right now, so it's got a -1. Nitrogen likes 5, but it's surrounded by 1, 2, 3, 4, 5, 6, 7. So it's got a -2 formal charge. Still too much negative. Let's go ahead and put a double bond someplace else. Sulfur's happy, so let's not mess with him. Let's just put a double bond over here and see what happens. Double bond over here. Okay. This lone pair is going to go away. Lone pair is going to go away over here because they helped form that bond. Now let's do formal charges. Again, we know sulfur is 0. Carbon likes to be surrounded by 4. It's surrounded by 1, 2, 3, 4. Nitrogen likes to be surrounded by 5. It's surrounded by 1, 2, 3, 4, 5, 6. Overall formal charge is -1. It matches our minus charge. Everything's following the octet rule. The central atom is 0. This is happy. Okay? If we added a triple bond here, okay, we would make the nitrogen 0, and this -1. This is the better formal charge, the better Lewis structure, okay, better resonance structure. So that is the answer to that one. Let's do one more, one that you'll see quite frequently, and then I will leave you with a challenge, and then we'll be done on formal charges. One that I happen to see all the time is XeF4. They love throwing xenon at you. Okay, xenon is one that is just an electron hog. It loves to be surrounded by electrons. So let's just get started. Xenon, okay, surrounded by fluorines. Let's put a bond to each one, and let's go ahead and put lone pairs around each fluorine. Okay, so all I can say is when you get farther down the periodic table like xenon, you most definitely can start putting lone pairs on that central atom. But first, let's just see what our formal charge is. Fluorine, 1, 2, 3, 4, 5, 6, 7. It likes to be surrounded by 7. It's got 7 surrounding electrons. All these fluorines have a formal charge of 0. Okay? And all I can tell you right now is that fluorine is going to usually be by itself on the outside. There's never going to be a double bond to fluorine. There's never going to be a double bond to chlorine. Okay? Those guys just like being on the outside with a single bond. Okay? They like just having a bunch of electrons surrounding them. Okay? They're super electronegative. That's what they like. Okay? You won't see double bonds to those guys. Hardly ever. Alright? So, and I already told you xenon's an electron hog. And right now, it's got a formal charge of, it likes 8, right? But it's surrounded by 1, 2, 3, 4 right now. It's got a 4 positive formal charge. So let's just go ahead and put something on it, like lone pairs, that'll give it a formal charge of 0. Okay? So if we want to give it 2 lone pairs, or 1 lone pair, it will now have a formal charge of +2. But if I just go ahead and give it another one, it now has a formal charge of 0. Okay? And that's totally fair because xenon doesn't follow the octet rule. It's really far down on the periodic table, so that means that it can have a bunch of electrons, right? I know this is crazy. There's a lot of exceptions. There's no straight up rules for it, but all we can do is use our formal charges to help us along the way. Main thing is that remember, fluorine follow the octet rule. They're usually on the outside with a single bond for the most part. Carbon, nitrogen, oxygen follow the octet rule. Everything else is pretty much up for grabs, okay? I would want to put sulfur in that octet rule, but it does disobey that rule sometimes too. Okay, so this is formal charges. I'm going to leave you with one challenge that is kind of interesting if you could figure it out. And then that'll be that. So go ahead and try O3, which is ozone. Ozone, okay? Give that a shot, hit pause, try it on your own, okay? And I will show you the actual formal charge for this guy. So, oxygen is just 3 oxygens in a row, right? If we started out with single bonds on each one, we'd have -1 here, 1, 2, 3, 4, 5, 6. We'd have 0 here, and we'd have -1 here. That's a -2 overall formal charge. We don't like that. Let's go ahead and put a double bond somewhere. Yeah, and they follow the octet rule, so I gotta get rid of lone pairs when I put in a bond. This is -1, 1, 2, 3, 4, 5. This is +1, this is 0. Okay? I could go ahead and I could add another double bond here, but that would just give me an overall charge of +2. So that's not going to fly. So really, the best formal charge one is this guy. But some of you may have thought, well, it doesn't have to be in a straight line. Couldn't I do this? And that truly is the best resonance structure, right? 0, 0, 0. The only problem is that it can't do that in nature. In theory, that's the best Lewis structure that you could possibly have. But it won't do this, okay? To make that triangular shape, it puts way too much stress on those bonds. Those bonds actually start looking like this, okay? And they put so much force on them that they actually break, and it reverts back to this actual Lewis structure. So, in theory, this is the best Lewis structure. But in the real world, that is actually the Lewis structure of ozone. Okay? That's it for Lewis structures. Get some practice, reach out if you have questions, and have a good day.